Hello everybody. We start with atomic physics. I recommend you to download this textbook. You can do this using this site. This is address and this is a link to this textbook. And exam questions are here. There are also questions to optics, and exam will include both optics and atomic physics. Unfortunately, atomic physics differs from all the physics we studied until now, and the problem is that the microcosm is different from ordinary world, and this difference is dramatic in a sense that the physics laws which we studied until now do not work at the level of atoms and other small particles. The point is that if we take some object and try to understand how it behaves in some processes, for example in mechanical movement, we can write down some equations and this object will obey these equations, and we can describe all the movement in frameworks of the theory which is based on these equations. And if we take a half of this body, these equations will be still valid and the result will be also adequate. We can take many small pieces of the same body, and for each of these pieces, again, all the physics will be the same. Unfortunately, such is not the case when we go to the micro world, microcosm, when we are at the level of microparticles like atoms, electrons, molecules. It appears that at this level, all this physical, most of the physical concepts which were used when we derived equations which depict whole behavior of the macro objects, these equations do not work, and this theory and these concepts do not work at micro level. We can ask me why is it so, and the answer is just because this is nature. Such is it organized, maybe such as it was created. We don't care how it was created at the moment, but nevertheless the point is that at the micro level the physics which we studied until now does not work. Here is a general plan of the course. First of all, we will follow some historical approach. I mean that we will study step by step all the studies, all the stages which physics went through, and until it arrived to the proper understanding of the physics which we call quantum mechanics. And we will see how it was necessary to change our understanding of physics because of contradiction between experimental evidences and results which we can obtain using classical theory. Then we will discuss new concepts which were introduced, and we will see that these concepts are in contradiction with classical physics. And finally, we will study quantum mechanical approach to the description of micro objects, and we will see that at this approach we can understand how this micro world behaves, and this is adequate depiction of micro objects. The problem is that unfortunately mathematics is the only way to describe physical behavior of the objects, and we cannot avoid to use a lot of mathematical constructions which we will apply to describe quantum mechanical objects. We will start our study of atomic physics with thermal radiation. Until now we studied light, and we did not care about the origin of light. We just mentioned that somehow atoms emit light. Historically, it appeared that thermal radiation was the first physical effect which was not possible to understand in the framework of a classical approach. What is thermal radiation? Well, thermal radiation is the emission of electromagnetic waves by bodies at the expense of their internal energy. Internal energy means that it is energy of thermal movement of particles which constitute body, and they are always in some movement, oscillations, and as a result some radiation occurs, and this radiation occurs at any body temperature. However, at the higher the temperature, the greater is radiation. At relatively low temperatures, radiation is mainly located in the infrared part of the spectrum, but at higher temperatures it becomes visible. Here you see, for example, we don't see this radiator, but we see sun, fire, and ordinary lamp. For example, here is photos in infrared rays of heat radiator, and if we speak about heat transfer, it can take place through the environment, as you know, through convection of air in this case, or heat conduction if you put some material on it, but also by radiation. You can feel that the radiator is hot even without touching it. The transfer of heat by radiation is produced by electromagnetic waves. In this case, the energy is converted twice. First, the energy of thermal motion of molecules is transformed into the energy of electromagnetic waves, and then, when the waves are absorbed by another body, the energy is transformed back to the kinetic energy of molecules. Thermal radiation is the only radiation. Not there are different ways to radiate some waves. For example, luminescence, chemical, but chemical of chemical origin. But when we speak about thermal radiation, as I just say you, that thermal radiation is transformation of mechanical mechanical movement of particles, which corresponds to internal energy of body, into electromagnetic waves. And it is the only type of radiation which can be in thermodynamical equilibrium with emitting body. What does it mean? Look, for example, we have some body which is enclosed in some enclosure, and this enclosure is maintained in some temperature. Imagine that this body is colder than the radiation in this cavity. In this case, all the time it emits some radiation and it absorbs some radiation. And in this case, if it is colder, the point is that if the body is warmer or hotter, the radiation is greater. So, in this case, we see that if it is colder than the environmental radiation, so it emits lower energy and absorbs greater energy, and as a result, the temperature is elevated. In the case we have a body which is hotter, the environmental radiation around this body, as you see at the right figure. In this case, the radiation will be greater than the radiation which is absorbed, and in this case the body will start to be colder until again equilibrium between radiation which is around this body and radiation which is emitted by the body is the same. So at any moment of time, the energy which is absorbed by emitting body is equal to the energy which is emitted, and this is what we mean when we say that there is equilibrium between emitting body radiation and the radiation of electromagnetic field, which is an enclosure of this body. And now, in order to work with this physics, we need to introduce some characteristics of emission. The first characteristic which we introduce is radiant emittance. Radiant emittance, we will denote it by R, is the energy flux emitted by a unit surface area of a radiating body in all directions within 2 pi solid angle. It is a function of the temperature and characterizes the emission of waves of all wavelengths or frequencies. Here we can you can see why we speak about 2 pi solid angle, because any body radiates only at the outer surface, not inside it. So this all the radiation which energy flux means energy per square centimeters per second, and if we it is total for radiation for all wavelengths. If we look at radiation of some particular frequency, so we have another quantity which is called emissivity of a body. We'll denote it with small r, and this omega here as index means that it belongs to some frequency in some small region around this frequency omega. I mean omega plus d omega. So it is energy emitted by a unit surface area of radiating body per unit time within unit frequency interval. You see, here is actually a relation between emissivity and radiant emittance. It is absolutely clear that in this case we can write down that this radiant emittance is integral of emissivity over all the frequencies. Here you see also a graph, a plot of this function, emissivity of a body. I mean R on omega. I don't see my mouse here. So R at omega, and this is experimental result. You see that it has some maximum at some omega, starts from 0 and goes to infinity. So we integrate from 0 to infinity this function, and area under this curve give us R of t. So radiant emittance, which corresponds to emission of all the wavelengths or all the wave of any frequency or wavelength. Now we need also a characteristic of absorption, and the characteristic of absorption is absorptivity of a body, and it is defined as follows. Let's assume that there is some flux d phi differential because it belongs to some interval of frequencies from omega to omega plus d omega, and in this interval of frequencies we have some flux of energy d phi, and some part of this flux is absorbed by the body, and we denote this part which is absorbed by d phi prime, and the ratio of this d phi prime to d phi is absorptivity of a body. It depends on frequency and temperature, and by definition it is always less than 1. So if a body is completely absorbing the radiation of all frequencies falling on it, in this case A is equal to 1. Such a body is called a black body. As a matter of fact, it is not easy to obtain in practice to obtain such a model of a black body. And the typical model which is used in physics is as is shown in this figure. Imagine you have some cavity with mirror or internal walls, and there is some small hole in this cavity, and if light enters this cavity, it will reflect it from the walls, but with a very small probability it will be possible that it will go back to this hole, and so practically, and it doesn't depend on the frequency of the light. So in this case we have a good model of a black body. By the way, you can see some if you look at the open window in a sunny day, it looks at black because light which enters this room is mainly absorbed inside and does not go out from this window again. Kirchhoff's radiation law, it states that if we look at the ratio of emissivity and absorptivity of any body, then it appears that it does not depend on the nature of a body, and it is the same function of the frequency and temperature for all bodies. Here you see this function, and ratio of emissivity to absorptivity is this function. Again, it doesn't depend on the origin of the body. Why? Look, If we have two bodies in enclosure and if they have initially different temperature and when time elapses they will have the same temperature, and in order because of equilibrium, which we already mentioned before, and in order they could obtain such a situation, it appears that in the case one of the if we need to reach this equilibrium, it appears that the body which absorb more energy should also emit more energy, and only in this case it can be at the same temperature. Otherwise it will be warmer or colder, and the only possibility to uh, to be in equilibrium is to have this ratio the same function and which does not depend on the origin of the body. The point is only that it should be in any by the way in any energy in any frequency interval, it should have the same ratio of r omega t to a omega t. This is typical shape of such function. By the way, if we assume that a omega t is 1, as it is by definition specific for black body, in this case we see that this function is just emissivity for black body. This emissivity, in this case, it is emissivity of black body. Sometimes in textbooks, emissivity or all the quantities which belongs to black body are denoted by asterisk. Well, look, in this curves we see that with temperature there are two specific features of this curve. First, we see that maximum is shifted to higher frequencies when temperature this is greater than z and this is greater than z, and in this case maximum is shifted right hand, and area under each of the curves is also increasing. This means that this value radiant emittance, which is integral of this curve, is also greater. This corresponds to so-called Stefan-Boltzmann law. It states that for a black body, radiant emittance is proportional to the force power of temperature, absolute temperature. Here, this sigma is some number, and this sigma is called Stefan-Boltzmann constant. For not black body, but just other emitter, not black body, this is not this constant. So this is correct. This constant is correct for a black body. What is important is that the radiant emittance of a black body is proportional to the force power of the temperature, and for any body it is proportional to the force power of temperature, but the coefficient is specific only for black body. The displacement of the maximum is also observed, and Wien's displacement law states that this displacement can be described by this formula. You'll see that actually the maximum wavelength, the lambda m, means the wavelength at which maximum of this curve is observed. Maximum of this curve is observed. So this is lambda m4, here is lambda r3, lambda n2, lambda m1. So this m means maximum, but maximum not wavelength, but maximum of this distribution of emissivity for function f. It doesn't matter whether it depends on lambda or omega. They connect. They have a known relation between them, and this means that this lambda m, the location of maximum of this distribution, is inversely proportional to temperature when b is some constant. You see that if we b divide by t, we see that this location of maximum and corresponding lambda for this maximum is inversely proportional to the temperature. Now let's consider Lambert cosine law. Imagine that we have two surfaces, two pieces of surfaces. One of them is here 1, another 2, and the position of this and that is different. We can consider these two parts of internal surface of some cavity, for example. And this cavity not necessarily is spherical, and this part of cavity is inclined against this one. Then we assume that this cavity is maintained at the same temperature, so all the pieces of the walls of this cavity has the same temperature, and consequently T1 is equal to T2. And then if we consider two similar surfaces with area S, then emittance and of both of them will be the same. Energy which is emitted from these surfaces will be the same, and the energy which is absorbed with the surfaces is also the same. This means that they interchange the energy between them all the time, and this means that this exchange should be equal. Imagine that I perpendicular is energy which is emitted from the surface, surface in the solid angle from this surface and from this surface. And this surface, C surface 2 under angle, this solid angle S over L squared cosine theta, when theta is angle, when normal is rotated against this line, which is between 1 and 2. And energy which is emitted by this surface is emitted not against along normal, but to this surface 1 is along this line, which is inclined by angle theta. So we denoted the energy which is emitted at this angle as I theta. And this energy is emitted in the solid angle S over L squared. You see, this is angle at which this energy which is emitted by S2 reaches surface 1. So energy which 1 emitted in the direction of 2 is here, and it is emitted along normal to the surface, and this is energy which is emitted by 2, and it is emitted at angle theta. As we already stated, this energy should be in equilibrium. They should equate each other. And just cancelling S L squared and squared, we have that the emittance of energy depends on angle, and the maximum of emittance is in direction of normal to the surface, and here is also to the normal to the surface. And in the case it is emitted at some angle theta, it is multiplied by cosine theta. This law works for diffuse surfaces which reflects light as diffuse surfaces. What I mean diffuse? For example, a surface of snow or sheet of white paper, not reflecting like mirrors, not polished surfaces. It works for such surfaces as I mentioned. Now, a very important point is a relation between radiant emittance from some bodies and radiant energy density. Let's again recollect what we mean. We mean that at the moment we wish to establish a relation between energy which is emitted from the surfaces of body and energy which fills this cavity. So the energy which fills this cavity is electromagnetic field in a form of electromagnetic waves, and energy which is emitted from the walls, we assume that it is emitted due to oscillations of electrons in the surfaces here, and these oscillators, they emit electromagnetic waves. And now we wish to establish a relation between radiant emittance, which we already defined, and the density of energy of electromagnetic field which fills this enclosure. Well, now we will consider emittance of energy from the wall of this cavity from one unit of surface, and we will separate here some surface in a form of sphere. This is just borders of this part of space, and we assume that this part of space has radius r, and it is spherical, and rho is radius of this cavity. Then when radiation is emitted from the surface in the direction of this space, it sees this part of space at a solid angle omega. And this solid angle omega is, according to definition, what is solid angle is PR squared over rho squared. PR squared is cross-section of the sphere. This is S divided by r squared. This is, as you remember, definition of solid angle. Then if we look at the density of energy which is created by this emittance inside the surface, then we have to remember that these waves are propagated here with the speed of light, and during some time of 1 unit, 1 second, this energy will fill such a cylinder which has a base of PR squared, and the height of the cylinder will be c, because c is the distance which will be covered during 1 second, and such a cylinder will be filled. But we cannot see all the cylinder, but in principle the density, in order to find the density, we have to understand that this energy is distributed somehow, so it fills, in principle it should fill this volume. Then if we multiply energy which is emitted from this point, this unit area of surface, in this direction, we must to multiply energy which is emitted. This is flux of energy which is emitted on the perpendicular to the surface, and multiply by omega. And if we divide it with this volume, we have consequently we have density which is of energy which of this field which is produced by this surface. Just if we substitute omega here and cancel what we can cancel, we arrive to this result. Now, in order to find real density of energy, we have to add all the energy which goes through this surface from all other points or other areas of this internal wall. This means that actual density U is density of energy of electromagnetic field inside this cavity is this energy, and we need to multiply this energy by all the surface. This is from unit surface area, so we multiply it but all the surface area of all the surface inside this cavity. This is result. So we obtained this result for density electromagnetic energy in the cavity through I perpendicular, where I perpendicular at given temperature is intensity which is emitted, intensity of radiation which is emitted along a perpendicular to this wall. Now we will leave this result for a while and look what we have with radiant emittance. For radiant emittance, we need to multiply if we have I theta. So if we have I theta, this means that we have intensity of radiation at a given angle theta. In order to obtain R of t, we remember that by definition R on t is radiation which is emitted in 2 pi angle and 2 pi solid angle. In this case, we need to substitute here. Now we remember from Lambert law that it is not isotropic, this emission. So we need to use instead of I theta, its value I perpendicular cosine theta, and this is solid angle. Now this is solid angle, and you understand that in order the solid angle cover the half of space, this theta is from 0 to pi over 2. Now if we integrate this, just substitute sine under differential and take this integral, you can check that it will result in pi perpendicular on C. Now let's compare what we have. We have now radiation emittance here, which is expressed through I perpendicular, and we have also here U on T, density of electromagnetic energy of electromagnetic field inside cavity, also expressed through I on perpendicular on T. Then if we compare these two results, we have that R on T is C, where C is speed of light, U on T over 4. This was obtained for all frequencies. We did not look at frequencies, but this equilibrium can be reached only if this is correct. This result, I mean this relation is correct for each of the frequencies. This means that we can go from this to Z, assuming that this is equal to radiation of the surface for the given small interval of omega. So it is emissivity of black body. So F of omega t is emissivity of black body. So for emissivity of black body, we have the same relation, that, and this function is this relation to u on omega. So now we have we understand how these two values correlate between what is relation between them. It is natural that when physicists study radiation, and experimentally it is not so difficult, and they obtained these laws like Wien's displacement, and they obtained this curve and dependence of these curves on temperature, and these curves, I mean F on omega, were measured with high accuracy, and it was absolutely clear that somehow we need to apply some theory and maybe to understand the laws and nature of the physics which corresponds to this radiation. Actually, what we have at the moment when this physics was developed, there was already very well established laws of thermodynamics and laws of electromagnetism. And what we have in this case, we have thermodynamics and heat exchange between surfaces and field, and we have electromagnetic waves. So all theoretical parts which are needed in order to understand what happens in case of radiation and thermal radiation were available, and consequently an approach is clear, and there was such an attempt to develop such a formula which would describe the effect observed in experiments. So I wrote here that the aim was to derive a formula for the density of energy of radiation here in the cavity on the basis of theory of electromagnetism and thermodynamics. So the object of consideration, the object under consideration was a cavity filled with electromagnetic radiation in the form of waves, which were emitted from the cavity walls by oscillating electrons, as I already explained to you. And the system was in the thermodynamic equilibrium with oscillation mean energy of kT, where K is Boltzmann constant. Now we try to understand why we say that average energy, mean energy, should be kT. Well, we have different waves, and these different waves have probably different energies, and oscillators which emit these waves as well have different frequencies and consequently maybe different energies. The question is how this energy of these oscillators is distributed on energy. How this energy is distributed per a given temperature. I mean, what is the probability to find the oscillator with some energy? We know that this probability is described by Boltzmann distribution, and this Boltzmann distribution says us that at higher energies, it is at given temperature, it is lower probability to find such energy for oscillator with such an energy. Well, Then, in order to find average energy, we have this probability function, and here is you see we E multiplied by this function. This gives us mean value if we divide it by all the possibility of this integral. Okay, this is maybe you know it from molecular physics where I studied it, but if we need to find some mean value, we need to multiply to take this mean value with probability which it acquire at each of energy, and probability multiplied by this energy, and then integral of all over this possible energies, and this is just normalization. Well, we made such a trick that we substitute it under d over d alpha logarithm. Look, if we what we have here, if we take this derivative, then it is 1 over this integral, a and a cancelled, and then we need to take again this derivative from denominator, and this is here is e goes there, and we have this. So you can see that this is equal to that. This trick helps us to obtain the result because it is easy to integrate this function. We integrate it from 0 to infinity, and then after simple transformations, we substitute here alpha as 1 over kt for convenience, and the result is 1 over alpha, so it is kt. So we obtain that the mean energy of these oscillators, or mean energy of all these waves, is kt for each of these waves. So if we look at now, if we take the number of these waves which are inside and multiply this number of waves by mean energy, we need in this case probably we will obtain the energy which is contained in this cavity. Now the question is how many waves are inside this cavity. It's maybe many formulas, but it is not so difficult to grasp what is here. Now we will, for simplicity, we will calculate number of waves in a rectangular cavity. So we have here a rectangular cavity with sides A, B, C, and located along x, y, z. And the equilibrium radiation is assumed to be established inside this cavity in a form, a system of standing waves. Indeed, how it can exist inside? Only if there are standing waves, and we have to know from oscillations and waves that standing waves, condition to standing waves to be established is that there should be integer number of half waves on the length at which it is located. So if we have 3 different sides, so for A we have lambda x over 2, it is the wavelength in the direction of x, and we remember that k is 2 pi over lambda, so if we substitute k instead of lambda, we have mx pi over kx, and from this we can say that wave number for waves kx is p pi over alpha mx, where mx is whole numbers 1, 2, 3, and so on. Absolutely the same is for another for B side along Y and along Z. This is C. So we have three numbers kx, ky, and kz, and these three numbers in different combinations they define or define the waves which can be established in this cavity, standing waves. Due to these whole numbers 1, 2, 3, we see that each of these numbers can be changed only by change of this by 1. So the smallest number of change is 1. So if we will consider some space of vector k. So if we consider the space of vector k, so here are the projection of k on x, y, and z. First, we need to take into account that these numbers are positive. So this vector can be only in 1/8 of all the surface in this only part of space, and the length of this vector can be changed only by some steps, and the steps is the steps in this direction is pi over a, in this direction pi over b, and in this direction pi over c. Again, look, if we change m by 1, the smallest step in change of case is here pi over c, pi over b, and pi over a. So if in this case we see that the smallest cell which is determined by changing of delta by 1 is v1 delta delta kx, delta ky, delta kz. So if we multiply them, we have pi and the power 3 divided by a, b, c. Again, this is small cell which is obtained if we allow k to change by the smallest step. Now, what is the whole volume? This is a volume of this small cell. What is the volume of this part? Okay, this is 1 over 8. I already explained y over 8, 1 over 8, because k is on projection are positive. And here is the volume of the sphere with length k3. So in this case we have total volume of this part as is shown here, and the small cell which corresponds to small changes of this k, the smallest changes of this k is v1. Now if we divide v0 by v1, we will obtain n total number of all the waves which are characterized by corresponding case. So we divide v0 by v1, and then we obtain this result. You can check it that it is obtained, and in some small frequency interval d omega. Sorry, I don't see my mouse at the moment. Okay, in some small frequency d omega region of d omega, there will be dn number of waves corresponding to this interval d omega, and this is just differential from this. If we take differential dn, here we have a differential from right side, and this is dn. And here is volume ABC. It is a volume, physical volume, not of this volume of this space, but physical volume of cavity. And this is dn, the number of waves which have frequencies omega in the interval d omega, around omega. Now let's again remember that the electromagnetic waves can exist in different polarization, and if they have arbitrary polarization, so we can decompose it into direction, a perpendicular direction. And as far as we consider only one wave, so we silently assumed that it was polarized in some direction. And actually, we should consider another wave which is polarized and perpendicular. Then we will take into account all the waves which can have different orientation. And this means that the actual number of dn should be multiplied by 2. Now, after multiplication, we have, if we took, look again, if we took this dn and divided by physical volume V, we will obtain density of this number of waves. D is dn divided by V, and we see that the density, so a number of waves per unit volume, is here. We started from the statement that if we have number of these waves and multiply by mean energy of each of waves, we will have a density of energy in the cavity. So what we will do, we will multiply it. Then if we take this density of waves, this is density of energy of waves in some volume, and multiply this by d omega, we have density of waves in the interval of frequencies from omega to d omega. Here we have average energy E multiplied by number of these waves in the unit volume in interval d omega. So we multiplied it, and what we have, we substitute here kt, which we already saw how it was obtained, and multiplied by this value, and we have this. So d omega here, and then we see that actually, as far as this is equal to that, we already found this correspondence between energy density of electromagnetic waves and emissivity of black body. We have the result, which is seen here. This is function f. This is experimental result. This is frequency on f. And we see that actually this f, which was obtained in the Rayleigh-Jeans formula, is proportional to omega square. So it is parabola. And this is a parabola. It agrees with experiment only at low frequencies, but it deviates from it, and moreover, it goes to infinity. So if you integrate this curve, you have some radiant emittance, and it is finite. But in the case you try to integrate this, what is under this curve, you have infinity. This small omega, it is correct, but at high omega, it is not. It is incorrect. By the way, higher frequencies corresponds to shorter wavelengths. So this problem, this confrontation between experiment and theory, was called ultraviolet catastrophe, because it was catastrophe for physics. Look, as a matter of fact, all this result which we obtained was based on a strict knowledge of existed at that moment physics. There was no assumptions which simplified the system to such an extent that the result of theory disagree with experiment dramatically. This theory was unable even to reproduce even approximately a real shape of experimental result. This was indication on some serious problems with understanding how in reality the process occurs in the case of thermal radiation. What is important at that moment is to point out that the problem is that we need to understand how these oscillators, which are on the micro level, behaves, which produces electromagnetic waves, and why it appears that somehow the result which we derive from strict theory of thermodynamics and electromagnetism, in which there was no problem at the moment the physicists tried to apply these laws to micro objects, how it appears that it was incorrect, and how and the main problem was how to overcome the problem. By the way, look how fantastically exciting is physics when people try to understand the laws of nature, and they see that there is no way to understand how it happens, and they need to invent some absolutely non-traditional approaches, and to launch new ideas, new concepts. By the way, it's not so easy to reject existing knowledge and to say that something is wrong and we need to introduce new concepts, which is very difficult to not only to explain, but in it even to understand. In order to overcome the problem, Planck launched a hypothesis that, as a matter of fact, this micro object, in this case electrons, they emitted absorbed energy not in continuous spectrum, as we assumed when we derived this kT as a mean energy of this radiation, but by portions which later were called quanta. And somehow he suggested that this smallest quantity of energy is h nu, or h bar omega. This letter is called h bar, and h bar is h divided by 2 pi, and h is called Planck's constant. It is just a number, and it is derived from experiment. But the point is that if this is the smallest possible value, and the next possible value is not something intermediate between h omega and 2h omega, but always energy is absorbed and emitted by portions. I mean h omega, 2h omega, 3h omega, but never 1.5 h omega. So the system can only have discrete set of energies. N is n h omega, where n is integer. Well, since the system is in thermodynamic equilibrium, we again repeat the same what we did for continuous distribution. We use Boltzmann distribution, but now, as far it is not continuous but discrete value, so we operate not with function of distribution of probability, but with probability itself. But probability itself should obey the same Boltzmann distribution. But here is En, where n means that E can accept only some discrete values, and these discrete values are n h bar omega. So we substitute it here. Now constant A can be found again from normalization. We just say that the probability that it has at least one of the frequencies is unit. So if we add all the probabilities, so the result is 1 because the system exists, so it has some probability, some frequency. So probability that it has some frequency is 1. Now we see then in this case A is what I wrote here, and Pn, when we substitute A, is here. Now we again repeat the same trick. We say that now mean energy is En multiplied by Pn. So we take En with weight of Pn. So we take each when we wish to find mean energy, we take each of this. Sorry again. We take all of these energies with probability which this is energy is observed. So now we substitute this En here. Here is En, you remember, and Pn is here. We did the same. We take and this is A. 1 over this is A. Again, we for a while we assume that this energy can accept some continuous values, just for mathematical simplicity, and we substitute here x, where x is h omega over kt, and why we assume that it can accept continuous values just in order to take differential from it. Again, we substitute it for the same approach with logarithm and derivative from this logarithm. If you take a logarithm from this, derivative from this logarithm of this, you obtain that. Now, why it is convenient? Because what is here in parentheses is this is a geometrical series, and we know the sum of elements of geometrical series, and in this case it is equal to that. Who don't remember this, look in handbook on mathematics, what is geometrical series and what is sum of all the terms of geometrical series. Now if we substituted the result here and make all these transformations, you can follow them yourself, check, and the final result is that mean energy in this case is here. Now we have again mean energy, and nothing changed with the density of waves. So what we need to do, we need to do the same what we did with Rayleigh-Jeans formula, but we have to substitute another mean energy, which was obtained in this concept that, as a matter of fact, the oscillators and consequently the waves which are emitted by these oscillators can have only discrete set of energies. Thus, we arrived to Planck's formula. We substituted this E, this mean energy, and the result is here. This is Planck's formula, and actually this formula appeared to be in very good, I would say excellent agreement with experiment. This is this function in variables omega t, and here is a function in the variables lambda t. How to go from this to that? Look, actually what is this? This is distribution of energy in some interval. The energy which is emitted in interval d omega corresponds to some energy which is emitted in interval d lambda. But this d lambda not necessarily is equal to d omega. They are different. And as far as they are inverse, look, so omega is left at the moment, left of the maximum, and lambda is right of the maximum. And if omega is 2 pi c over lambda, then the d omega over d lambda is here. And this minus just means that when d lambda is larger, d omega, when it's increasing, d omega is decreasing. And but what is important? The important is that this area corresponds to energy which is emitted in d omega, and this area is energy corresponding to emittance in d lambda. But this energy should be equal to each other. So f omega t d omega should be phi lambda t d lambda. Then in order to go from omega variable to lambda, we need to, from here, we need to multiply it by d omega over d lambda, and we obtain this result. So this is a curve in this variables, and this is a curve in that variable. Why we made this transformation? Because it is sometimes more useful for practical point of view. For example, from Planck's formula, all properties of thermal radiation are reproduced by Planck's formula, and as one of the laws which we already considered, I mean Wien's displacement law, we can find maximum of this function, phi lambda t, maximum of this function, and to find how this position of this maximum depends on temperature. And it appears that we will arrive exactly to Wien's displacement law. For this case of Stefan Boltzmann, we have just to integrate all this curve over all the frequencies from 0 to infinity, and we will obtain the formula sigma t in this fourth power. And by the way, we will obtain some theoretical value for sigma, so we will understand what is the origin of this coefficient, which we call Stefan Boltzmann constant. As we see now from consideration of thermal radiation, in order to obtain understanding, to reach understanding of the physics of the phenomenon, we were needed to apply some concept which is very strange, and it was the first time that it was discovered that some continuous behavior of known values like energy and we will see later other, including coordinate, is incorrect when we proceed from our ordinary world to a microcosm. So this is the end of the first lecture of atomic physics.